No sooner did Michele dry her eyes over Cassini's fiery end than she turned her attention to Jupiter. We are proud that Michele's team's magnetometer for the Jupiter Icy Moons Explorer, JUICE, of the European Space Agencies was the first part of the mission completed and is ready for launch in 2022. Michele has been duly honored for her work. She has been very appropriately awarded the 2008 Hughes Medal of the Royal Society, quote, for innovative use of magnetic field data that led to discovery of an atmosphere around one of Saturn's moons, and the way it revolutionized our view of the role of planetary moons in the solar system. In 2012, she was elected a Fellow of the Royal Society. She was awarded the 2017 Gold Medal of the Royal Astronomical Society for Geophysics, and last year she was awarded a CBE in the 2018 New Year's Honors List, and she received the Institute of Physics Richard Glazebrook Gold Medal and Prize. Please join me in welcoming Michele Dougherty to the podium.
Good evening, everybody. Lovely to see you here tonight. What I'm going to talk to you about this evening is really an overview of the Cassini spacecraft mission at Saturn and its moons. And I always like to start with this particular image here because it shows you the Saturn system in its entirety. You can see the sun or sunlight peeping out from just behind Saturn. You can see the beautiful rings, so the visible rings, which are clearly seen even if you look at Saturn through a telescope from the Earth. And you can also see a very diffuse ring called the E-ring around here. And if you look really closely, you can see a moon that's embedded in the E-ring. Now, this consists of lots and lots of pictures that were taken over a long period of time and put together as a single image. And so you can actually see the moon on numerous occasions. You can see it there, and you can see it there as well. And one of the things I'm going to talk about this evening is this moon called Enceladus, and how my team discovered an outgassing of water vapor from this moon, which actually goes towards making up this E-ring. And you can actually see some of the outgassing in the images that were put together. And the last reason I like to show this slide is because you can see the Earth. The Earth is just there. And that always makes my hair stand on end, knowing that Cassini turned around, took a picture not only of Saturn, but took a picture of us on the Earth as well. We didn't always know a lot about Saturn, and in fact, I remember my first view of Saturn was when I was a child in South Africa. My dad built his own telescope. He actually ground the mirror. My sister and I were really proud of ourselves because we mixed the concrete for the base of the telescope. And I remember seeing a little round ball with what looked like rings around it. And it was similar, actually, to the view that Galileo first had of Saturn way back in 1610. And the telescope he was using wasn't very good. And so to begin with, he couldn't quite work out what he was seeing. There were times when it looked as if there was a moon on either side of Saturn. On other times, it looked as if the moon had actually joined to the planet itself. And much later on, it looked as if there was this strange solid ring around Saturn. And it was only about 45 years later when Christian Huygens realized that instead of it being moons on either side, it was actually a set of rings around Saturn. And the reason that they couldn't tell what it was to begin with is because as Saturn orbits around the sun, its inclination is quite high. It's got a 22-degree inclination to its orbital plane. And so depending on where it is in its orbit around the sun, sometimes it's at an inclination to the Earth, and other times it's side on. And if it's side on, you simply can't see the rings at all. And in fact, Christian Huygens also discovered Titan in the same year that he worked out that it was rings. And so this was Christian Huygens' sketch of Saturn, where he proposed that it was surrounded by a solid ring. And there was some more work done later by Cassini, who actually realized that there was a gap in the ring, and that's known as the Cassini division. And the Cassini spacecraft actually flew through that gap when it first got to Saturn back in 2004. Now, you can't have a spacecraft mission as large as Cassini without a lot of international participation as a result. And this shows you all the different countries that were involved, not only in building the instruments and helping build the spacecraft, but also doing the science that came back from the instruments as well. On the magnetometer team, we had scientists in the UK, in Germany, and from Hungary, and also from the States as well. Now, this view of the spacecraft shows you it in its entirety. You can see the Huygens probe. This was built by the European Space Agency, and when we got to Saturn, the Huygens probe was detached from the Cassini spacecraft and actually traveled down through the atmosphere of Titan. I'm going to talk a bit about Titan to you in a short while. You will also notice that most of the spacecraft seems to be covered in a gold foil, and that's a thermal blanket that helped to keep the instruments in the spacecraft at a temperature that they could actually operate in. This white umbrella-shaped object is the high-gain antenna, and once we got to Saturn, once a day, the high-gain antenna would turn and face the Earth for 8 hours, and it would send back all of the data that it took in the previous 24 hours. And then last but not least, most importantly from my point of view, is the magnetometer boom. What we do is we measure the magnetic field in the environment of the spacecraft, but we're actually wanting to measure it from Saturn or from Jupiter, depending on where you're going. So we want to make sure we get as far away from the spacecraft as we can, so the magnetic field we measure is due to the environment and not due to the spacecraft. And so what we do is we get ourselves put on a very long boom, and so the instrument that we were responsible for consisted of 2 different instruments. One of them was built at Imperial College, and it was placed halfway down the boom, and the other one, which was built at the Jet Propulsion Lab, was placed on the end of the boom. And in fact, one of the things that happened about a year after we reached Saturn is the instrument on the end of the boom stopped working. And that made life rather complicated for us because we needed to calibrate the instrument, and I'll talk about that in a while. This shows you a view of the Cassini spacecraft in the test chamber before launch. I always like to show this because it gives you an impression about how large the spacecraft was. You can see people, and these are actually real people, standing at the bottom, so you can see how large the spacecraft was. It was about 6 stories tall, weighed about 7 tons before launch, and you can see very clearly the gold foil that essentially covered the spacecraft in its entirety. The reason that the spacecraft and the instruments were put into the test chamber so we could test to make sure that they operated in the vacuum environment that they would find in outer space, but also so we could thermally test them as well. Because as I'm going to show you, for us to be able to get out to Saturn, we had to actually go into the inner solar system to begin with. We flew past Venus twice, where the temperature's about 40 degrees Celsius. And once we got out to Saturn, the temperature's about minus 170 degrees Celsius. So we needed to make sure that the instrument and the spacecraft could actually operate in that kind of environment. One of the things that you might notice is the magnetometer boom isn't there. And that's because you can't launch a spacecraft with a boom sticking off from the side. Or you could try, but it probably wouldn't be there for very long. And so what happened is the boom was deployed and folded away in this canister here. And when we flew past the Earth during our interplanetary cruise, we actually deployed the boom. We know the magnetic field of the Earth really well, so that then allowed us to help calibrate the instrument. These are the 2 instruments that went up towards making the instrument suite. This is the one that was built at Imperial College. It's a fluxgate magnetometer. And this is the one that was built at JPL, a vector helium scalar sensor. And in fact, one of the exhibits outside later will be from some of the engineers who were building the instrument that's going to Jupiter. And they were also involved in the instrument that was built for Cassini as well. Now, one of the things about magnetometer sensors is what we need to know is we need to know where the 0 level of the field is. If you've got 2 instruments, you can use them to intercalibrate between each other. If you've only got one working instrument, which is what we were left with a year after we reached Saturn, you need to roll the entire spacecraft around 2 separate axes to be able to calibrate. And that was a really interesting test of the collaborative nature of the Cassini team, that the teams actually allowed us to roll the spacecraft so that we could calibrate, because it took away from their science as a result, but it enabled ours. So this is the interplanetary trajectory. What we're doing is we're essentially looking down on the equatorial plane. We have the sun off to the left. We have, you can see the orbit of Venus in there, the orbit of the Earth in there. This is the orbit of Jupiter, and this is the orbit of Saturn. You can't launch a spacecraft as large as Cassini with enough fuel to get straight out to Saturn. And so what we do is we use planetary flybys. It's almost a slingshot. What you have is if you get close enough to a planet, you get into its gravitational field. If you're moving in the same direction as the planet is moving, you can gain energy from that interaction. If you're moving in a different direction, you lose energy, and it actually allows you to slow down. And that's what we did when we first arrived in orbit around Saturn. We were moving in a retrograde orbit, allowed us to slow down and be captured by the gravity of Saturn. So what we did is we were launched on the 15th of October, 1997. We had first Venus flyby in 1998, the second Venus flyby in 1999, and then we had a flyby past the Earth in 1999 as well. And then the final flyby was past Jupiter at the end of December 2000 before we finally got out to Saturn. And it took us almost 7 years to get out to Saturn. You need a lot of patience to be involved in interplanetary missions. As Alice mentioned, the Cassini mission was first thought about back in 1982, and it only ended in 2017. And so you need to be able to be working on other things as well, because otherwise you would spend your entire career waiting for a sort of mission to start. Okay, so we reached Saturn on the 1st of July, 2004. And there are 3 things I'm going to talk to you about this evening. I'd like to talk about a lot more, but there is no way I'll have enough time to do that. So the first thing I wanted to talk to you about was Titan. Now, this was a view of Titan that was taken by the Hubble Space Telescope, and this is another view that was taken by Hubble Space Telescope as well. And one of the first things that you'll notice is that you can't see the surface. And that's because there's not only a very dense atmosphere at Titan, the blue region here is the atmosphere, but its surface is covered by an ethane-methane photochemical haze. And so you can't actually see down onto the surface. And so it was only once we got there with Cassini and Huygens, using particularly the infrared, that you could actually see through the haze and see down onto the surface. Now, one of the reasons that we were really keen to get a better understanding about Titan is that we thought its atmosphere was very similar to what the Earth's atmosphere was like when it first formed. So it was almost like a way of going back in time and getting an understanding about how our atmosphere has evolved from when it first formed. And so what happened is that when we first went into orbit around Saturn, the Huygens probe, the European Space Agency Huygens probe, was deployed from the Cassini spacecraft and traveled down through the atmosphere of Titan and landed on the surface. But in addition to that, there were many flybys by the Cassini spacecraft of Titan. We flew past Titan about 120 times, and so we now have a much better understanding of Titan. This shows you a view that was taken by the imaging instrument on board Cassini when we were really close to Titan. You can see we were doing slightly better at seeing down onto the surface. There's in fact a highly reflective region here called Xanadu, and that was the only region which had actually been glimpsed in the Hubble Space Telescope images before Cassini got there. But you can still tell that we're not really seeing the surface in very much detail at all. But it does show you very beautifully how deep the atmosphere is. It's about 950 kilometers in height. And in fact, when we flew past Titan on all of those flybys, we had to be really careful that we didn't get too deep into the atmosphere because the density was pretty high. And with the magnetometer boom sticking off from the side, we were really concerned that the spacecraft might begin to tumble. So we had to be really careful that we didn't go too deep. Now, one of the real surprises in the first 5 years of our orbital tour at Saturn was the fact that we were not finding any liquid on the surface of Titan. The Huygens probe, when it traveled down through the atmosphere and it landed on the surface, took beautiful images as it was going down, and it noticed there were lots of dry lake beds and looked like grooves where liquid of some kind had been flowing. But for the first 5 years, we couldn't find any liquid at all. But then, in 2009, the VIMS instrument, which is the Visual Infrared Mapping Spectrometer, saw this flash of sunlight glinting off a liquid lake on the North Pole of Titan. And that's when we suddenly realized that it was related to the seasons on Titan. Before this, it was in the northern hemisphere as Titan was in winter darkness, and so the sun was not getting anywhere near the North Pole of Titan. But as we moved into mid-2009, we were moving to equinox, and that's when the sun's rays were beginning to get to the North Pole, and that's when we saw that glint from the liquid on the surface of Titan. And in fact, it turns out that it was coming from the edge of a lake called Kraken Mare, and I'll show you a picture of the lake shortly. But it was only because we hadn't had any sun in that region that we hadn't been able to see any of the liquid. And in fact, when I talk about liquid on Titan, I'm not talking about liquid water, I'm talking about liquid methane. And so it's a very strange place. So this shows you 6 views of Titan, again from the VIMS instrument. It's 6 infrared images of Titan that were taken over the entire 13 years. So it was data taken over 13 years that were put together into these different images. And I'm going to point out some of the surface features. So this is that, I always get confused with buttons. This is the Xanadu region, that bright reflective region that we could see in the imaging instrument, but also was faintly seen in the Hubble Space Telescope Hubble Space Telescope observations. This is a highly reflective region. Let's see what else we have. Down below, we have this circular region, bottom left, which is called Hotai Regio. We think this is an ice volcano, so we think that liquid is coming up from underneath the surface of Titan and moving out of the ice volcano and freezing as it gets to the surface. One of the clear things you'll see is this dark brown equatorial belt. You can see it on all of the images. It almost completely encircles Titan, and this is filled with dark brown organic sand. There's a little crater here that you can see called the Synlap crater. That's about 80 kilometers across. And the other thing you'll notice next to it are these violet regions here, and you can see them on other parts of the surface of Titan as well. And this is where there is a lot of water ice on the surface. The largest known crater on Titan is called Minerva. That's in the bottom left-hand image there, and that's about 400 kilometers across. And then if you have a look at the North Pole, you can see, we actually seen from a lot of the images that most of the lake features are at the North Pole. And you can see one of them here. This is Kraken Mare. This was where the glint of the sunlight from the edge of the lake was seen in that 2009 image. But you can also see there are some more lake-like features in the image above that too. And then last but not least, there is a single footprint-shaped lake at the South Pole, which is called Ontario Lacus. And so our understanding of Titan is increased 1,000-fold compared to what it was we knew before we went there with Cassini and Huygens. And there's some plans to try and send future spacecraft missions to Titan to get a better understanding about what is going on the surface, but also get a better understanding of the atmosphere as well. So let me move on to what is probably my favorite moon of the moment, Enceladus. Maybe when JUICE gets to Jupiter, I'll change and something else will become a favorite moon. But before I talk about the moon, let me just describe briefly what the data is that the instrument measures. So what we do is we measure the magnetic field, which is a vector. And so what we do is we measure the 3 components of the magnetic field, and we add those together, and it allows us to work out the strength of the magnetic field, but the direction that it's pointing in as well. And so if we have a planet like the Earth, the same thing happens at Saturn and Jupiter as well. If you stand on the surface of the Earth, the compass needle is going to point to the North Pole of the magnetic field. One way to think about the magnetic field, we know it's generated in the deep interior. It's a little bit like having a dipole magnet in the deep interior. If you think about it, if you had a piece of paper, you had a bar magnet underneath a piece of paper, and you put iron filings on top, those iron filings are going to lie along the lines of force of the magnet. And that's essentially what we're seeing here. If we could see the magnetic field of the Earth and of Saturn, then this is what the lines would actually look like. The other thing I'm going to want you to keep in mind when I tell you about the discovery that we made at Enceladus is that as the planet rotates on its axis, the magnetic field lines are going to rotate at the same rate. And so if you're a moon somewhere in the Saturn system, as Saturn orbits on its axis, on its rotation axis, the field lines of Saturn are going to be moving towards the moon. And that's one of the things that I'm going to touch on when I show you the data. So let's just orient ourselves as to where Enceladus is. So we have Saturn off to the left with all of the visible rings. We've got the very diffuse E ring that you saw in that first image that I showed you. And you have some moons orbiting around Saturn. So this is Enceladus, which is what we're going to be talking about now. But you can see there are other moons close by. There's a moon just inside of Enceladus called Mimas. There's one called Tethys and Dione, and Titan is way off the board here, way off the page. Now, one of the things we knew before Cassini reached Saturn is that the particles in the rings are made up mainly of water ice. And the other thing that we knew is that Mimas, which is quite close to Enceladus, is covered in lots and lots of craters. But the surface of Enceladus didn't look the same. And so when we got there and we took that image, the imaging instrument took, well, those two images and put them together of the surface of Enceladus, the first thing that you'll notice is there are hardly any craters at all. Implication being that something is resurfacing it. Why is the surface as young as it seems to be compared to the moons that are close by? The other thing I'll learn right at the end of the talk, I'm sure. The other thing that you'll notice is you've got these very deep cracks on the surface as well. We knew that Enceladus was within the E-ring. People had long wondered whether Enceladus was somehow the source of the E-ring, but no one had been able to work out how it could be the source. Now, when the Voyager spacecraft flew past Enceladus back in the early 80s, the infrared instrument on the Voyager spacecraft took an image of the surface, and they were able to tell from that image that the surface is made up mainly of water ice. Now, we had 3 flybys of Enceladus planned in 2005, so about 7 months after we reached Saturn. The first flyby took place in February of 2005 and was just under 1,300 kilometers away from the surface. There was a second flyby planned a month later, which would be 500 kilometers away. And then there was a third flyby planned about 4 months after that, which was another distant flyby. It was 1,000 kilometers away. Based on what we saw in our first 2 flybys, we were able to persuade the project to take us much closer on that third flyby. And I'll show you what data it is that we used to persuade the project to do that. I'm trying to think if there's anything else I want. Yes, the other thing I wanted to say here is one of the other things to keep in mind about Enceladus is it's pretty small. Its diameter is only 500 kilometers, and so its gravitational field isn't very strong. So you have to be a magnetometer person to get excited about magnetometer data. But we have some magnetometer people in the room, so I thought I would talk you through what the data looks like. So this is data from the first Enceladus flyby, which took place in the 17th of February 2005. What you can see is the 3 components of the magnetic field, the top 3 panels, and the magnitude, the strength of the magnetic field along the bottom, and it's 24 hours worth of data. This here is the main dipole field. If we have the equivalent of a bar magnet inside at Saturn, you would expect to see a very strong north-south field, and that's essentially what this component is telling you here. This here is the radial component, and it looks as if there's something a little bit funny going on there. This is the azimuthal component, and again, there seems to be a very strong signature there. Those of you with good eyesight or sitting close to the front will notice there's a little pimple in the data, just there and there. That was the flyby of Enceladus. The other thing that you will notice is that the data seemed to get very noisy, just as we were approaching Enceladus and as we were flying away. And what we were able to do is to use that noise in the data to be able to work out what molecules, what ions were generating the activity that you can see in the data. So just because it's difficult to explain this data to someone who doesn't work with it every day, what we did is we put it into a different format. So what we did is we subtracted the background magnetic field of Saturn away from the data. So what we were focusing on was the result from Enceladus. Here we're looking down on the north pole of Enceladus. Saturn is off at the top of the building. The magnetic field lines and the plasma from Saturn, as it rotates around Saturn, were coming in from the left here. And this shows you the trajectory of the spacecraft. Overlain on top of the trajectory are the little magnetic field vectors that are left once you subtract the magnetic field of Saturn away from the data. And it looks a bit strange. It's almost as if the magnetic field is sensing an obstacle that is much bigger than Enceladus is itself. Something seems to be stopping the magnetic field of Saturn from actually getting down onto the surface of Saturn, of Enceladus. Sorry, I'm talking about too many different bodies tonight. Getting down onto the surface of Enceladus. And the other thing, I mentioned this on the previous slide, there was this very large increase in ion cyclotron wave activity. We analyzed the data, and what it was telling us is that as we were approaching Enceladus, there was a very big increase of water group ions as we got close to the moon. So what could do that? What could stop the magnetic field lines of Saturn from penetrating down onto the surface of Enceladus? And this is we put this little movie together to try and understand what was going on. So there are two different aspects to it. First of all, we're looking down. Here our eye is looking down on the north pole of Saturn. So there's the north pole of Saturn. Saturn is the yellow ball. The gold circles are the rings of Saturn. The blue lines are the magnetic field lines of Saturn, rotating at the same rate that Saturn is. And the little orange ball is Enceladus. If Enceladus was a dead body, the magnetic field lines wouldn't see it at all, and they would move straight through it, just as you can see in that view there. What we seem to be seeing, though, and now we're looking sideways on, what we were seeing is here was Enceladus. The magnetic field lines of Saturn were moving towards it, but weren't able to get down onto the surface. Something was stopping them from getting down onto the surface. And one of the ways in which you can do that is if you have an atmosphere. The upper regions of the atmosphere become ionized by solar radiation, and that then stops the magnetic field from being able to penetrate down. It happens at the Earth. The upper regions of our atmosphere are ionized, and the magnetic field lines from the sun can't penetrate down. So what we did is we put this schematic together, which was essentially showing what we thought was going on. So we have Saturn off to the left. We have the magnetic field lines of Saturn shown in blue. And then we have Enceladus here with a diffuse extended atmosphere covering the entire surface of Enceladus, which was essentially not allowing the magnetic field lines to penetrate down onto the surface. Now, if this was true, this was a real discovery because, as I mentioned earlier on, Enceladus is a very small moon. We saw it on two subsequent flybys. We saw it in the February flyby and the March flyby. And if there was some outgassing of some kind taking place, it needed to be going on continuously because we saw it on the two separate flybys. Because if it wasn't, the gravitational field of Enceladus wouldn't have been able to keep the atmosphere in place. And at the back of our mind was always the thought, maybe this is what's feeding the E-ring. Let's see if we can understand what's going on. So because we knew that the third follow-on flyby was going to be 1,000 kilometers away, we didn't think that would solve the issue for us. And so what we decided to do was I flew out to the Jet Propulsion Lab and I made a case. I was going to make a case to the Cassini project and the scientists that we should lower the third flyby to take us really close. And I was really quite nervous about doing this because we weren't absolutely certain that we were seeing this in the data. We thought we were seeing it. But one of the problems was that as the spacecraft flew past Enceladus, it was moving really quickly so it could keep Enceladus in the view of the cameras. And we were slightly concerned that maybe we hadn't received the best trajectory of the spacecraft back yet. And maybe our calibration wasn't right. But also the other thing in the back of my mind was one of the things that we spent the 6.5 years it took us to get to Saturn was to plan every second of the first 4 years of the observations that we were going to make. So if we were going to go in and ask for the flyby trajectory to be lowered, that would actually take away some science that some of the other teams were planning to do. So I was jet lagged to hell. The meeting was at about 10 o'clock and I arrived at JPL and I needed a coffee. And so I went and I stood in the line to buy a coffee, and standing in the line in front of me was a guy called Jerry Jones, who was responsible essentially for driving the spacecraft, but also for the safety of the spacecraft. And he was quite surprised to see me. He wasn't expecting to see me there. And he asked me why I was there. And I told him, and his eyes lit up. And he said, I've always wanted to go closer to a planetary body than anyone else. And I thought, I've got one person on my side. So I went into the meeting still nervous, but not quite as nervous as I'd been before. It took quite a lot of persuasion. Not everyone was convinced, but the general consensus was that we should do it. And so the Cassini project agreed that we would lower the third flyby to 173 kilometers above the surface. We would use a bit of our spare fuel to actually do it. And fortuitously, and you'll see why I say fortuitously now, the flyby was planned to come up below the south pole of Enceladus. And so I didn't sleep for 2 or 3 nights before that third flyby, because if we hadn't seen anything, no one would ever have believed anything I said again. So when I saw the data, though, I knew that we had made a real new discovery, because what we saw was not that there was an atmosphere covering the surface, but in fact, there was an outgassing of water vapor focused just at the South Pole. And this water vapor, as it was coming out from the South Pole, was becoming ionized, and it was that which was stopping the magnetic field lines from being able to penetrate down onto the surface. But because we went so close, all of the other instruments were able to take great data as well. And so I'm going to show you data from some of those instruments now, which underpinned what it was that we had found. So, top left is an image from the imaging instrument on board Cassini, which shows you the entire surface, or at least 1/2 of the entire surface of Enceladus. And you can see there were cracks in the northern hemisphere, a few more craters from what we'd seen in that first image. But the real surprise was these very deep blue-colored cracks at the South Pole, which the imaging team called tiger stripes. Bottom left is data that was taken by an instrument that was able to remotely sense the temperature of a planetary surface. What they expected to see was that the hottest region would be at the equator, where the solar radiation was strongest. Well, when I talk about hot, this is all relative out here. We're talking about 65 to 85 degrees Kelvin. So out at Saturn, that's quite hot. It's about minus 100 degrees Celsius. So what we actually saw in the data was, yes, there was a hottish region close to the equator, but there was actually a hot spot, almost 20 degrees Kelvin higher than we expected to see, right at the South Pole. And if you overlay these two data sets on top of each other, the hottest spot at 91 degrees Kelvin was right over one of these cracks. And so the implication was, what we were seeing is had internal heat, which was leaking out from the center of Enceladus. Real surprise. As I've said on a number of occasions, Enceladus is really small. We had always thought it had long since cooled down from when it first formed, so it should have been really cold. But instead, there was this internal heat source, and the internal heat was leaking out. This shows you a view that was taken by the imaging instrument about 6 months later, when the camera turned back and looked at Enceladus, and you can see the vast extent of the plume. The different colors show you the different densities, but if you look really closely, you can almost tell that there are different source regions. Here and here, just underneath here, we've got different source regions, and I'm actually going to show you in a subsequent slide that we think there are different sources along these cracks, and they tend to open and close depending on where Enceladus is in its orbit around Saturn. This here shows you a view, a combination of data, imaging instrument view, but also a temperature map as well. Just to orient you, that there is 50 kilometers, so it gives you an idea of the extent of what we're seeing. And these little stars here are different sources. And as I've just mentioned, we think these sources open and close. And the reason they do that is as Enceladus orbits around Saturn, its orbit is not quite circular. So on some parts of the orbit, it's closer to Saturn than on others. And so the tidal forces from Saturn are stronger. And that, we think, is what's causing these different sources to open and close. This here is a real close-up view of one of the tiger stripes. And as you can see, it's two parallel ridges. The width is about 5 kilometers across. The height of the ridges on both sides is between 100 to 150 meters, and the depth, the V-shaped trough that you can see, is about 250 meters in depth. And it's within this trough here where these sources are opening and closing over time. If the fact that we had internal heat leaking out of Enceladus and water vapor, and therefore liquid water underneath the surface, wasn't exciting enough, we also found organic material. On one of the subsequent flybys that we had of Enceladus, because we focused on Enceladus a lot after 2005, one of the instruments called the ion neutral mass spectrometer was actually able to taste almost what was in the plume. And so we flew through the plume, and this is what it found. It found water vapor, which we weren't surprised about because we knew it was there. We had seen it in our data. It found carbon monoxide and carbon dioxide, methane as well, and then simple and complex organic material. And this is when people really became excited about Enceladus, because one of the reasons we go to the outer solar system is to try and get an understanding about whether there is the potential for life to form somewhere else. You need 4 things. You need liquid water, you need a heat source, you need organic material, and you need those first 3 things to be stable enough over a long enough period of time that something can actually happen. And it's that stability over time that we're not sure about at Enceladus, but we have at least 3 of those 4. The other exciting thing, and I haven't got it in this slide here, but on an even later flyby, the INMS instrument found ammonia in the plume. And at these great distances from the sun, so at these very low temperatures, ammonia can act as an antifreeze. And we think that might be one of the reasons why we're able to have liquid water at these very great distances from the sun. And so following on from the Enceladus discoveries that Cassini made, there's now a real focus on searching environments where you can get liquid water underneath the surfaces. Before the Galileo mission to Jupiter and the Cassini mission to Saturn, scientists had always focused on planets close to the sun where we hoped we would find liquid water on the surface. But now we know we can find liquid water underneath the surface. And so it opens up the search for potential habitability. And that's one of the focuses of the Jupiter mission, JUICE. So in the last 10 minutes or so, I'm going to talk about the end of mission for Cassini. So we were in orbit around Saturn for 13 years, but about 11 years in, we realized that we were going to run out of fuel. The fact that we had lasted as long as we did was a testament to the planning. We wanted to make sure that we didn't crash land on one of the moons of Saturn, because if life was ever discovered there in the future, we didn't want people to be able to turn around and say, but a man-made object landed on the surface. And so what we decided to do is that we would crash land in the atmosphere of Saturn and the spacecraft would be broken up. But we thought, let's do that, but let's try and get the best science out that we can. And one of the things that we did not understand about Saturn, and we're still trying to get our heads around it, is how its internal planetary field is generated. At the Earth, we understand that what you have is something called a planetary dynamo. You have a convective overturning motion. Heat is given off, a bit like porridge bubbling on a stove. But you also have an internal rotation as well. And those two processes combine to form a planetary dynamo which generates the field. But what planetary dynamo theory tells you is the rotation axis of the planet and the magnetic axis of the planet have to have an angle between them. There has to be a tilt between them. If you don't have a tilt, you can't continue to generate the field. When we reached Saturn, the magnetometer team thought it would find what the tilt was in the first 4 years. 13 years in, we're still trying to get our head around the fact that we cannot find a tilt between the rotation axis and the dipole axis. And so we don't know how the magnetic field is generated. So there were 2 phases to the end of the mission. Here is Saturn. This is the orbit of Titan, and Titan was used as a gravity assist to bring the spacecraft up out of the equatorial plane. The first phase was known as the ring grazing orbit, where the closest approach was just beyond the edge of the visible rings. And we were in that orbit for about 6 months, and we learned a lot about the environment here so that we could understand what we saw when we got close. And then the last 6 months of the orbit was this grand finale phase, the orbits in blue, where we were essentially inside of the rings and just above the cloud tops. Our closest approach was about 3,000 kilometers above the top of the atmosphere. And then the final orbit is this orange orbit that you can see there. One of the things we needed to keep in mind about this is the spacecraft was never designed to do this, and the instruments were never designed to do this either. And the fact that we only had one working instrument meant that when we were really close to Saturn, we had to roll the spacecraft around closest approach. And that took quite a bit of persuasion to get that. So this shows you a close-up view just to show you how close we got. It also shows you very nicely that Saturn's rings are not solid. They're actually made up of countless individual particles, each in their own orbit around Saturn, and you can see that there. So here we were skimming just above the cloud tops. And one of the reasons we wanted to do this is we wanted to try and work out what is going on inside Saturn. We know that we've been able to measure these field lines outside, but how is it being generated? Planetary Dynamo says there needs to be a tilt. The measurements that we are making are showing that there isn't a tilt. When Pioneer and Voyager flew past Saturn, it measured a tilt less than 1 degree. The early Cassini observation said the tilt was less than 0.06 degrees. The end of mission results are showing it's less than 0.0095 degrees. So it's effectively not there, and we still don't understand how that can be. What we think might be going on inside is we have a solid core, and then we have the dynamo region, which is fluid metallic hydrogen. So electrons are stripped off, and that allows currents to flow, and those currents then generate the field. So our next steps are, we're now going to start putting all the data sets together from the end of mission, gravity data, radar data, the mag data, to see whether we can try and understand what's going on. And we've actually organized a 3-day meeting with the Royal Society over the summer to bring all the experts together and the Planetary Dynamo experts to see if we can find out what's going on. So this shows you an artist's impression of the first dive between the rings. And I actually went out to JPL for this. We were really nervous because we didn't know what was in between the rings. We thought there might be some highly energetic dust particles which could do damage to the spacecraft. Because when we first arrived at Saturn and we came up through the Cassini division, we came up with a high-gain antenna pointing in the direction of travel, and we did hit some energetic dust particles, and there were some holes left in the high-gain antenna ever since. So we did the same when we started the end of mission scenario to try and protect ourselves if there was any energetic dust. So I remember we were all sitting there waiting for the data to come back from this first orbit. And the project manager came up to me looking really nervous, and he said, "Oh, I'm nervous." And I said, "I'm nervous too." He said, "Oh, I'm not worried about the spacecraft, I'm worried about you guys." And I said, "Oh, thank you very much," because of course, we were here. We weren't being protected by any high gain antenna at all. But we survived. There was nothing there. It was called the Big Empty. There was no energetic dust material between the gap at all. And so that meant on the subsequent 21 orbits, we were able to change the orientation of the spacecraft so that we didn't have to worry about protecting ourselves. So this shows you where Cassini dived into the atmosphere. This is a view from the VIMS instrument again, which is showing you at 5 microns in the infrared, and you can see the heat of the interior of Saturn, and the dark regions are cloud structures. Just to orient you, it dived into the atmosphere just above the equatorial region at about 2 o'clock in the morning on the 15th of September. That shows you a view from the operations room after the end of the mission. It was really interesting, you know, people were saying to us, "You're going to be really sad when it's over." And most of us were saying, yeah, we know. But we were also quite relieved because those end of mission orbits happened every 6.5 days. And it was exhausting. And we just couldn't keep up with the data. So we were all rather blasé about how we were going to feel. But seeing that made you realize how important this was to people. But I think for me, the most poignant moment was, this is a view again from the same room, but in the top left here, you can see the connection to the spacecraft. There's something called the Deep Space Network, which allows the spacecraft to talk to the Earth. There are lots of places on the Earth where you can actually talk to the spacecraft. And these are 2 different frequency bands. And as long as there was a spike in those 2 frequency bands, it was telling you that the spacecraft was talking to the Earth. We knew once those spikes disappeared that was it. And so we were all sitting there watching the spikes, and the top one disappeared first, and then the bottom one disappeared, and we thought, okay, that's it. And then the bottom one came back again briefly. And that was because no one had told the spacecraft that this was it. The spacecraft had been programmed to talk to the Earth. And so it turned itself so that it could continue talking until eventually it began to tumble and it couldn't do it anymore. And that's when it really hit me, actually, that it had gone and it wasn't coming back. So to end, I'm going to show you a movie which JPL and NASA put together before the end of mission started, which describes what it was we were planning to do. And I still think it's spectacular that the mission survived all the way through to the end. So I'll stop talking and I'll leave you to watch the movie.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini Spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a 1 million-mile trek to Saturn. We have cleared the tower. Its program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
Down to the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Wasn't that fantastic? Can you hear me? I'm not sure that I'm on. Okay, wasn't that fantastic? Michele has agreed to answer some questions from the audience, so we'll take those before we do the real thanks. So, who would like to ask a question? There's some microphones floating around. So here we go, down here. Why not?
Enceladus is producing
Keep your hand up if you want to.
is producing heat to make to power the plumes. It shouldn't have enough heat energy to do that. What's the current thinking on how it's doing that and what the heat source is, the origin of it is, and how long will it last?
It depends which theorist you talk to, of course. But we think it's because its orbit is not quite circular. And so we think tidal heating is doing it. So on some parts of the orbit, it's closer to Saturn than on others, and that's keeping the interior warm. How long it lasts? I think we're just fortunate that we're there while it's happening. It must have been going on since the 1800s, because there were some ground-based images taken of Saturn where you could just see the rings, and they saw some funny features in the rings, which was probably the E-ring. So it's been happening since the 1800s. When it'll end, I don't know.
There was another hand here.
You were part of the NASA team. Is such an arrangement that you have ad hoc, project by project, or is that institutionalized? And part B of that is, what is your next thing? Which planet?
The way in which you get selected for spacecraft missions is you propose. And so the former principal investigator, David Southwood, who was here before I arrived, he proposed to build the instrument for Cassini, and he formed an international team to do it, and they chose our team to do it. The next mission I'm involved in, and I have a confession to make. I primed this gentleman because I met him beforehand, and he said, "Oh, you're going to tell us about JUICE?" And I said, "Well, if you ask me a question."
Cheat.
Well, I thought if there's one occasion when I can cheat, this is it. And this is called JUICE. It's a dreadful name. Alice reminded us what it's called, Jupiter Icy Moon Explorer. You've got to really get your head around the acronym, but it's there. And what it's going to consist of is a spacecraft launched in 2022, which will get to Jupiter in 2030. I won't tell you how old I'll be. It will spend 3 years in the Jupiter environment, probably more, but for me the most exciting part of it is it's going to go into orbit around a moon called Ganymede. And Ganymede is an absolute paradise for people who are interested in the magnetic field, because Ganymede is the only moon in the solar system that has an internal dynamo. But in addition to that, it's embedded in the background magnetic field of Jupiter, and that causes currents to flow in a liquid water ocean. So you can actually see, this is Ganymede here. We think there's a liquid water ocean underneath the surface of Ganymede. And we're going to be able to measure the fields that are generated by the currents that flow. It also gives me nightmares, though, because the signals we're going to try and measure are really small. And I was saying to Tom earlier, we had tea earlier, and I was saying it's like trying to find needles in a haystack where the needles are changing color and shape all the time. So you can ask me in 2030 if we've been able to do it or not. But thank you for asking me that question.
We will, of course, change the name to Jupiter Imperial College Explorer any day now. So, yes, I can see a hand here.
Gosh, you've got better eyes than me, Tom.
Thank you for a fascinating talk.
Hello.
Hello. And the Enceladus, I know, is your pet subject. I just wonder if there are any plans to investigate this water vapor from the southern pole, and how is it affecting?
You keep dropping in and out. Sorry.
Right. How that manages to affect the magnetic field from Saturn? It seems quite a small eruption of water vapor for that to happen.
It's not that small. You saw that image I showed. It's about 100 kilometers above the surface. But, you know, the instruments we build here are so sensitive it can see even small perturbations. People want to go back to Enceladus, but to be able to do it properly, to be able to understand it properly, you need to go into orbit. And it's really hard to go into orbit around a little moon that hasn't got a very strong gravitational field. You need a huge amount of fuel to be able to do that. So they hope to do it in the future.
Good, thank you.
So I'm going to steal Chair's privilege for
Of
the
course,
last question.
I assumed you would.
So when you see parallel ridges like that on Earth, it immediately reminds you of a rift, of things moving apart. Mm-hmm. Is there any evidence that that's what's happening?
Not on Enceladus yet. But on one of Jupiter's moons there is. One of the moons is called Europa. And if you have a look at some of the images of the surface of Europa, it looks very similar to what you see when you look out of an aeroplane window and you fly over Greenland. There are these bits of ice that are breaking off from the main ice crust, and we think moving on liquid water.
So, please join me again in thanking Michele on the most incredible presentation. As you heard from Alice at the beginning, we're now going to play you a short video about the Schrödinger students. I think. I'm looking to see if there's someone running around in a panic at the back. Oh, is there? Well, here we go. Problems of the world. We need to have people who have been completely unencumbered in what they choose to study. Which one of those dark rooms do they go into? Those kinds of people are the kind of people who will be able to help us solve the problems of the world. If we spend all of our time being directed at the things that we think are a problem today, we won't solve the problems of tomorrow. And the freedom that this scholarship gives is to generate, as I said before, those really great scientists who really will solve the problems of the world. Either fortunately or unfortunately, you got about 30 seconds of the video. I think we'll give up at this stage. And also, contrary to popular belief, I hate the sound of my own voice. So all you need to know now is if you leave by the doors on either side, there'll be people there to guide you to refreshments. Thank you very much. Schrödinger changed the world.